I'll go back to full screen. I don't know if that's helpful for y'all or not, but in case it is. Okay. Any questions, issues, comments since last time?
No, sir.
Okay. Now, I always put the roll sheet where we left off, so I'll know where to do, and I put it on the wrong page. I put it where we left off when I was giving the assignments. I didn't put it where we left off in class. So I think we're if you have a text on page 9, this is chapter 1, Introduction to Differential Equations, section 1.1, definitions and terminology, which seems like it's going on forever. But there are a lot of terms here you don't use in any other field except differential equations, so it's sort of, well, may use it in some, but we were doing example 8 at the bottom of page 9. We had done the A part, I remember that for sure, and I thought we had started and done something on the B part, but I'm not sure we finished it. Is my memory correct, or am I out to lunch? Well, I may be out to lunch, but that's beside the point. Where did you have that we ended? Maybe you don't have books, so you don't even know what I'm talking about.
I have it where we just finished doing example 8.
Okay, the B part also.
Yes, sir.
Okay.
It kind of cut out, and it made it sound like you were underwater, but I can hear you fine now.
Yes, I forgot to drain my swimming pool last night, and it overflowed, so never mind. No. There's one thing I did want to, this is the part I did not remember doing on 8. I thought we worked through 8 okay, but I think we were running out of time, and I may have rushed it at the end, okay? So just as a quick review, I think we had done this. We saw that they told us a 2-parameter family. I couldn't find my piece of paper I wrote on, so I'm writing again. And I'm using ink, which is not a good idea, but I'm using it. Y is equal to C1 e to the x plus C2 x e to the x. That was an explicit solution to the differential equation y double prime minus 2y prime plus y is equal to 0. Now I wish they were telling us how they got that, but that's going to be a couple chapters away. Sorry about this. I don't know why the book is organized this way. And I remembered that we did verify that, okay? And I think that's what you indicated too, right? We did take the first derivative, the second derivative, and then plug those in and found out we did get that solution, right? Am I remembering correctly? Now, in my last class, students told me when I turned my head to look at my book, I faded out. Are y'all experiencing that?
Yes.
Okay, so I'm going to move my book to be right on my computer, so I'll always be talking to the screen. So sorry, I wish y'all had said something earlier, okay? Now, did you remember that we did verify that solution? There's your solution. See, I can see it now, okay? There's the solution for that differential equation. See if I can get them both on the screen at once. It's going to be awfully small, okay? And didn't we go through and take the first derivative of this solution, the second derivative of that solution, plugged it in here, found out it was indeed equals 0. My memory is that we did, but I've taught this course so many times I may be flashing back on myself. Did y'all remember that?
Yes, sir. I have that.
Okay, good.
In my notes, we did that full problem.
Right. Now, what I didn't do, or I don't remember doing, and tell me if I'm wrong, I think I did show the picture in the book of some of those solutions. You can see that picture okay?
Yes, sir.
Now
Yes, sir.
here's where the book made an error. Okay? Now that is, and I'm going to set it down again for just a moment and explain something I don't understand of what they're talking about here. They say underneath B, they say, in that figure that I just showed you, we have shown 7 of the double infinity of solutions. Okay, now I know what they're talking about. The double infinity of solutions. That's a number of solutions. I thought they were talking about double infinity solutions. I said that doesn't make sense. The double infinity of solutions in the family. Now, what they mean by that, that's a strange way to express it. But you see, because you have an infinite number of C1s and an infinite number of C2s, that's why they're calling...
Out again.
What's that?
Cut out again when you held the textbook up.
I'm cutting out? Okay, I'll try to hold it above my head. The book kind of blocks my speech. Is that better?
Yes, sir.
Okay. Thank goodness you can't see me. Okay, I'm talking under the book. See, there I am. Okay. What they mean by double infinity of solutions, you have an infinite number of solutions for C1 and an infinite number of solutions for C2, and then they're compounded because you have any combination of those infinite number of solutions. Weird way to say it. That was confusing me. But then they say, of those solutions, they are mentioning the red, green, and blue solutions. Okay? Now, I don't know if you can see it well enough. I'll get it as close as possible. See, the red comes in from the left and heads up when you're heading to the right. Okay? The blue does the same thing. It dips a little further, but still heads up to the right. And then the green comes in, dips up, if you call that a dip, and then heads downward. I said, that doesn't make sense with what they say next. Because what they say next, now do any of you have the book?
Yes, sir.
Oh, you do? Okay. You'll notice there they say the red solution is y is equal to 5x e to the x. In other words, the C1 is 0 and C2 is 5. That's the red solution. Okay? And they say the verbiage down here, but that's really hard to read, I'm sure. There's where they're talking about it. Okay? The blue solution is when C1 is 3 and C2 is 0. That's the blue solution there, which is those values there, I think. It's really hard to see, okay? Somewhere there, okay? Now, what threw me is the green solution heading in the opposite direction, but then I looked at it and they put the things wrong, okay? The green solution is what they list here. Here's Dawson coming in. Hold on a moment and let me get Dawson in the class. Okay. Dawson, we saw you come in. Have you made it to the microphone yet?
Yep.
All right, good deal. Good morning. Okay. So I'm guessing we got 4 of you here. Okay. Now, Dawson, we're on, if you got a book, on page 9, chapter 1, Introduction of Differential Equations, 1.1, Definitions Terminology. I think you have an ebook, so you probably don't have page numbers, but it's example 8, B. We were working on this last time, but I did note an error in the book. Okay, and I think you see where I made the correction to it. See, the green goes downward where blue and red went up. Okay, now, the reason they got the equation right there, you see the blue equation? They say y is equal to, I can't read the number, 5 e to the x minus 2 x e to the x. But then they say over here where C1 is equal to 5, but C2 is equal to 2. That's supposed to be a minus 2. Okay? I don't know if your book has that same error, but that should be a negative 2 there. I'm sure y'all were worried about that and concerned as you were reading that, so I wanted to ease your fears. They just did a typo in the book. All right. But the whole reason to show that is that indeed there are graphical solutions for every one of those combinations of C1 and C2, that double infinity, they call it, number of combinations. They just picked 7 of them to show the graphs. They only told you what 3 of those choices were. Okay. Any questions on that? All right. Now, for ebooks, this doesn't make sense, but for the rest of you, hopefully it does. Turning over to page 10, there is another definition here of sorts. And to me, it's almost confusing, and I bet you I will sometimes say them backwards just because it's sort of a nitpicky little point. Okay, let's go back for a moment. When you have a differential equation, first order differential equation, you have what we call a 1-parameter system. Okay? When you have a second order differential equation, you typically are going to have a 2-parameter system. Now, the general solution is when those parameters, however many you have, are in there. However, a solution, and this is back on page 9, a solution for a differential equation that is free of parameters is called a particular solution. There's that definition right there. Let's pull it back just a tad. I don't know, yeah, there. A solution, I'm trying to get it so you can read it all in the same line. A solution of a differential equation, blah, 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 that is free of parameters is called a particular solution. So for instance, when they put in values down here, that gave particular solutions. The general solution was the one where you had the parameters in there. When they put values for the parameters, those are particular solutions. All right? Not a big deal, but that's more nomenclature, terminology, definitions. But on page 10, they say sometimes a differential equation possesses a solution that is not a member of that family of solutions. Okay? That is, the solution cannot be obtained by specializing any of the parameters in the family of solutions. If you do specify those make particular solutions. But for those that you can't, that such an extra solution is called a singular solution. So a particular solution has no parameters, but that's because you put values in for the parameters. A singular solution is a solution that has nothing to do with the parameters. Okay, does that kind of make sense? Hope so. Maybe not.
Yes, sir.
Okay, good. All right. Now, flashback. I don't want to have to write all this again, so I'll hold it up. Okay. Do any of you not have a book? Because I want to show the book if any of you don't have that, but if all of you have the book, you can read along with me. So, do any of you not have a book yet? Because I have some classes that hardly anyone has a book yet. They're still on the order or whatever. Do all of you have books?
I have one.
Okay, that's Melissa. Billy?
Yes, sir, I have it.
Oh, you do. And I know Dawson does, right?
Yep.
Okay, Cole, how about you? Cole, do you have a book or an ebook? Cole, are you there? Have we lost Cole? No, he's still here, I think. His microphone's still on. Cole, do you have a book? Maybe you can't hear me. Say again? Yes, you do? I can't hear.
Yes, sir.
You do? Okay. So all 4 of you have books. I'll quit showing the book. I'll just refer to it then. Okay? So I'm going to, I don't know what's best. For now, I think I'll just move this thing somewhere down here out of the way. You probably can't see what I just did, but it was right in the middle of the screen. Okay, so I'll quit holding up the book except if I want to specialize. So you see on the top of page 10, or for those who are ebooks, you probably can't tell the page number, the definition of a singular solution. And you see also there they give the example. Y is equal to 1/16 x to the fourth. That should sound familiar because we did this back in, where was that? I think that was example 5, top of page 7 if you have page numbers. Okay? We saw that was a solution to the differential equation dy dx is equal to x y to the 1/2. And that was the A part of example 5. Okay. Now, they say that later, section 2.2, a long way away here, we shall demonstrate that by actually solving it, the differential equation dy dx equal that, x y to the 1/2 possesses the one parameter system of solutions. Now, this is probably a part we did not do in, So, I'll write this out for you. Hate to do it again, but we will. I'm going to use ink, even though it's not as convenient as that. It just shows up better. So we know that y equal 1/16 x to the fourth, but also y equals 0. Both are solutions for dy dx is equal to x y to the 1/2. Now in 5a, we did that. Okay, so, this was one solution. Here's another solution, both for this differential equation here. Now what they're going to do, just out of the blue, and they say in section 2.2 we'll find out how to do this, which we will. Here is the general solution, the one parameter family of solutions that is the general solution. Y is equal to 1/4 x squared plus c squared. That now, is now, am I fading out now in volume? Someone let me know. Have I gotten hard to hear? You can still hear me?
It's kind of difficult to hear.
Okay. I can't believe the paper is blocking that much of the sound. How about this? Is that better? Still not good?
Still difficult to hear.
Okay. Let me try this then. How's that? Is that better?
A little bit better. It's not,
A little better.
but I think the paper's blocking it. I think it's because you're turning your head away from your microphone.
Okay. Well, I'm turning so I can see the screen of where I'm placing this. Let me try this. I don't know if this will work, but let me try it. Let me see if I can move this block here. Down there. Okay. You can't see what I did, I don't think. But now, is this better on sound?
Yes, sir.
Okay. All right. There is the general solution, one parameter, C, if I can find my pen here. Okay. This is really an awkward way to have to teach. Okay. All right. Yeah, here we go. Okay. There's your one parameter, C, and you certainly see that this solution, y is equal to 1/16 x to the fourth, certainly fits here, because when c is equal to 0, you square this thing, you get 1/16 x to the fourth. So that's a solution. But y is equal to 0 there's no c you can put in there that's going to make y equal to 0. Now, this is a particular solution. Y is equal to 1/16 x to the 4th. This is not a particular solution because no value for c makes it. This is what we call a singular solution. It just happens to be a solution that doesn't fit our parametric solution, our general solution. That's what we mean by a singular solution. All that for that one illustration. Okay. Now, let's move on. Example 9. Are there any questions about that?
Why is it a solution if it doesn't work?
It does work. It just doesn't fit the general solution.
Got it. Okay.
Yeah, it is a solution. If you put y equals 0 and take the derivative of y with respect to x, that's 0, okay? And you plug that into x, you can put any value in there, but the square root of 0 is 0, so 0 is equal to 0. That is a solution, but it doesn't fit our family of solutions, okay? So that's what makes it a singular solution. It is a solution, but it doesn't fit the family of solutions, our general solution for the differential equation. Okay. So, does that answer your question?
Yes, very
Okay,
much so.
good. All right. Now, example 9. Here's a function. X equal, now they've changed variables on us now. X equal C1 cosine 4t and x equal C2 sine of 4t. Okay, there's two solutions. One with C1 and one with C2. Arbitrary constants or parameters, okay? Both are solutions for this differential equation, x double prime plus 16x is equal to 0. Okay? Usually they say verify, okay? Let's do a quick verification unless you want me to slow down, and we'll do it slowly too. Let's take that first one. Okay, notice there's no derivatives in the no first derivatives in the differential equation, just a second, but we still have to take the first derivative to get there. So x prime would be, correct me if I'm wrong, minus 4c1 sine 4t. Yes or no?
Yes, sir.
Okay. So x double prime would then be minus 16 c1 sine 4t. No, cosine 4t, sorry. Let me write them down because it's hard to remember. x1 is equal to 4c1 sine minus 4c1 sine 4t, and x double prime is equal to minus 16 c1 cosine 4t. Agreed? There's the original solution. There's something that's aggravating here. Okay, that's better. Okay. Had that little symbol in the middle. I don't know if you could see it, but it was bothering what I could see. Okay. X equals c1 cosine 4t. Well, you take the first derivative, that's a minus 4c1 sine 4t. Take another derivative of that, and you get a minus 16 c1 cosine 4t. Okay? Well, put that into this differential equation, x double prime, which is minus 16 c1 cosine 4t plus 16x, well, x was c1 cosine 4t, yeah, minus 16 blah, 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 plus 16 blah, 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 same blah, blah, blahs, that's equal to 0. So that obviously fits. You do the same thing for this one. X prime would be 4c2 cosine 4t, and then x double prime would be minus 16 c2 sine 4t. Okay? And sure enough, when you put that in for here, x double prime minus 16 sine 4t, C2 sine 4t, and plus 16 times C2 sine 4t, that adds to 0 again. So sure enough, both of those are solutions. They didn't tell us to verify, but it's usually a good idea to do so. Okay? Now, for that first one, x equals C1 cosine 4t, the first two derivatives, and they tell us they go through the same thing we just did. Substitute back in, you see they're equal to 0. Okay? Now, why? Yeah. They just did the same thing we did. Okay, sorry. I didn't realize they were going to do it. Finally, it's straightforward to verify that the linear combination of solutions of the two-parameter system, in other words, take those two solutions you know to be true and then make the linear combination, which would be x equal C1 cosine 4t plus C2 sine 4t. That is going to be your general two-parameter system. The linear combination of those two solutions that we had here. If I can get my fingers out of the way, that is also a solution. Because if you take the first and second derivatives, you get the same things because they're not related to each other. They're independent of each other, and you get the same. That's a solution. Now, I don't know why they entitled this problem using different symbols, except the fact they put the independent variable, the dependent variable x and independent variable t. I guess that's why they did it. But the most important thing here is that what we just illustrated was if you have two separate solutions for a differential equation, then the linear combination of those. And when I say linear combination, it's any constant times the first plus or minus any constant times the second. That will be a solution as well. Okay? Later, we're going to call that the superposition principle. Why they didn't say it here, I don't know, but it is indeed true. All right? Now, the next example shows that a solution of a differential equation can be a piecewise defined function, which usually are pains in the neck or some other body part, but we won't get into that. Let's see what they mean by that. Here is, okay, and by the way, I wanted to say this. I think I've said it before, but I just wanted to point out. Remember that example we just did? There's your differential equation. X double prime plus 16x equals 0. The fact that it's a second order differential equation requires us to have two parameters. So it's not at all surprising you have two independent solutions here, but the linear combination, that gives you your two-parameter system. Okay? Hint, don't look for any more independent solutions. If it's a second order differential equation, you only need two independent parameters. Okay? Arbitrary parameters. They didn't make a point of that there, but that's true. We've said it before, wanted to point it out. It was still true here. All right, so example 10 gives a one-parameter family of quartic monomial functions. Okay, what a name there. That is y is equal to c x to the fourth. Quartic means it's a fourth degree polynomial. Okay, but it's monomial, it's only one. That's an explicit solution to the linear first order equation x y prime minus 4y is equal to 0. Okay? And they say it's on the interval from negative infinity to positive infinity, which kind of makes sense because it's a polynomial. Polynomials are defined everywhere. Okay? So they do say for this one, verify. So how would we proceed to verify? What's the Jesus answer? Take a derivative. Y prime, if y is equal to cx to the fourth, what would your y prime be? 4cx to the third. Perfect. Okay? Now, let's plug that y prime back into the differential equation. Differential equation is x times y prime, which is 4cx cubed, minus 4 times y. Well, y was cx to the fourth. The question is that equal to 0? And it doesn't take a lot of imagination to see that indeed that is true. Because if I can find my pen here, it's somewhere. Where is it? Okay. The pen should show up someplace here, and it hasn't yet. Where in the world is the pen? There it is. Okay. All right. If you do 4cx to the fourth, distribute that x inside here, minus 4cx to the fourth, that's equal to 0. Sure enough, that's a solution. And because it's a first order differential equation, here, well, there it is. There, see, only one prime, first order differential equation. You only need one arbitrary constant. C is all you need. Okay? So, don't look for another one. So we just verified that is a solution, and because it's a polynomial equation, it's a solution everywhere. No problem. Now, okay, if you got your books, you can see in the left margin, I assume this is the same on ebooks, right next to example 10, you'll see one of those solutions when c is equal to plus 1. That is it looks like a parabola, but it's flatter on the bottom than a parabola. That's the graph of a quartic solution, okay? When c is equal to 1, that's your x to the fourth. When c is equal to minus 1, you have exactly the mirror image of that, but it's opening downward rather than opening upward, okay? That's the red graph, okay? So those are two possible solutions, okay? And they're good for minus infinity to infinity. They certainly work, okay? But here's another one that works. And I think I will use the book because I don't like to draw in the air anymore. Okay. If you came down with I'm going to do it opposite the way the book did, came down with the blue function here and came to here, but then paused and went to the red function here, that would be a solution. Or, as the book did, start with the red function here, come up here, and then pick up with the blue function. That's a solution. Okay? Now that means you have a piecewise solution. And here is that piecewise solution. Your y is equal to minus x to the fourth when x is less than 0, positive x to the fourth when x is greater than 0. You can put your equal sign with either one of those, and they're continuous, perfectly fine solutions. But you see there your solutions, another solution could be a piecewise solution. That's what they're talking about here. Now, if you put another c in here rather than 1 up here, if the c was 2, that's going to be a vertical stretch of that. So one of those could be stretched vertically. You could not put that in the bottom, and you could still make two linear combinations of those because they all meet at 0, 0. Okay? So there's actually an infinite number of piecewise solutions you could put. There's just one of them. the simplest one, so to speak. I can't get the book to stay still. Okay. Hard to hold. Okay. Now, let's move on to systems of differential equations. Don't sweat this much because they just mention it here right at the end of the section. I'm not sure we ever pick it up again. Okay? But in theory, as well as many applications, we sometimes have to deal with systems of differential equations. Now, am I correct at assuming that most of you are pre-engineers? Yes or no?
Yes for me.
Okay, Cole's yes. I know Dawson's yes. Melissa?
I'm getting a degree in pre-med, but I'm getting a degree in engineering, but I'm pre-med.
Oh, I see. Okay. You're going in the medical, biomedical or something like that?
Yes, sir. I'm biomedical engineering. And
Exactly.
pre-med.
Excellent. Okay, great field. And Billy?
I'm a junior industrial and systems engineer.
Okay, all right. So all of you are more engineering oriented. I was going to say pure math majors would be doing this too, but the engineers, it makes sense because you have systems out there that have all kinds of inputs and other things going into them. I'm thinking specifically industrial engineering, something like that, but mechanical, that would work, electrical, that would work. You could have several things that have to be met at the same time, that everything has to fit together. That would be what you described with a system of ordinary differential equations, because just about every twist or turn that you have probably could be represented by a differential equation, and if they all have to work simultaneously, then you have a system of ordinary differential equations. Okay, and they show you a sample of that. Dx dt is equals some function of t, the independent variable, x, one of the dependent variables, and y, the other dependent variables. Okay, now why is that not a partial? Why is that a regular derivative there? Only one independent variable. That's what makes the difference between partials and regular derivatives. If you only have one independent variable, you deal with regular derivatives. If you have two or more independent variables, that's where you have to get into partials. You have two or more dependent variables, no sweat. You stay in ordinary because you only have one independent variable, t. And then because you have a second dependent variable, y, as a function of t, that derivative is some other function, g, of t, x, and y. Okay? So the solution of such a system as that is a pair of differential functions, phi1 that satisfies one and phi2 that satisfies the other, defined on the common interval, okay, that satisfy each equation in that interval. So basically, you come out with two solutions there. Now, earlier we said a first order differential equation only has one arbitrary parameter, but if you have a system with different dependent variables, each one has its own. They don't list an arbitrary coefficient, but the phi would have some arbitrary coefficient in it, phi1 and phi2. Now, we get to our first remarks. The remarks are at the end of every section, and frankly, they seem like they just love to muddy the water with these remarks, okay? Maybe it's necessary, and maybe some of you will run into these. I imagine you will, but you probably won't remember them from here. Sometimes when you're trying to find that, and this was true for antiderivatives as well, trying to find what that function is, you may find it very difficult, sometimes impossible to do. You just know that that solution function f of x is some integral of some other function. That integral may be a non-solvable integral. Okay, there are some of those. Okay. If you then turn around and take a derivative of this is just basically your fundamental theorem of calculus part 1 or part 2. I can't remember. I think it's part 2. The second part of that, okay? It just says take a derivative of it, you get the function that's on the inside. Yeah, that's from fundamental theorem of calculus. They don't say part 1 or part 2, but it's they call it part 2. Now, if that integral could be solved, then that is what we call an elementary function. But if it can't be solved, the integral of that g of x does not have an elementary function antiderivative, then we call that just an integral defined function. And you have packages that do those for you. You can buy them, your businesses will probably have them if they do them. You don't have to worry about how you solve them. You just solve them numerically usually. Now, what do we mean by elementary functions? They list them. They say most of the things you studied in pre-calculus course. Constant functions, of course. Polynomial functions, of course. Rational functions, which are ratios of two polynomials, yes. Exponential functions, yes. Logarithmic functions, yes. Trigonometric functions, yes. That would be all 6. Inverse trigonometric functions. And basically, finite combinations of those functions using addition, subtraction, multiplication, division. Okay? Even compositions, function compositions. However, sometimes those compositions especially get you into situations you just can't solve. Okay? And they give some examples there. E to the minus t squared, if that was what you had as a function, it looks pretty simple. You're never going to be able to integrate that because there's no substitution you can make. There's no integration by parts. There's no technique in the world that will solve that. But it still represents something that's very real in nature. Basically, your bell curves. That's what that comes from, okay? The square root of 1 plus t cubed. Sounds pretty simple. If that was a t squared, there's a trig substitution you could do to solve that one. But 1 plus t cubed, nothing you'll find will ever integrate that function. So even though the function itself may be elementary, the integral of that function is easily not elementary. Cosine or sine of t squared. That's an elementary function, but its derivative is not. Non-elementary. And again, I don't think we're going to run into any of these, but that doesn't mean that in your work life you won't run into any. So just stand by for that. I'm going to skip most of the rest of these, but on page 12 or the next page or whatever, the very last one, they talk about something that I've been using the term already, general solution. If every solution of an nth order ordinary differential equation, ODE, f of x, y, y prime, y double prime, all the way up to y to the nth equals 0, that's one way to express an ordinary differential equation, okay? On some interval I, you always have to have the interval, maybe infinity, but you have to have it, can be obtained from a n-parameter family of solutions. Remember, if it's nth order differential equation, you need n parameters. So your solution then would be g, and of course x's would be in it because that's your independent variable, but then you can also have y's in it, but you don't have the derivatives, but now you have all those parameters, C1, C2, C3, C4, all the way up to C to the nth. If you can find that, that is called your general solution. Now that's written in such a way it doesn't look at all familiar, but we'll run into that many times in the future. Okay, that finishes 1.1, thank goodness. Okay, homework exercises here. If you got your books, you can see them here. Any of the odd numbers, 1 through 7, if their answers are in the back of the book, and they say they are, they say I've selected odd number problems, but most of these in the first part are usually back there. Any of those that are, do some of them, just so you get familiar and say, yeah, I've got this. Then move on. Do number 9. It's a slightly different type. Do either 11 or 13. Okay? Do either 15 or 17. Do 19. Slightly different. Okay? Then do either 21 or 23, or both. If you want to do both, you can do both. That's fine. Either 25 or 27. Try to do 29. That's one of those piecewise defined functions. Either 31 or 33. Do 35. Do either 37 or 39, and do 41. Now, if you can't do them all, don't sweat it, but try to sum in each group, okay? Now, remember the dean, former elementary school teacher, wants to have assignment, I think maybe for either every week or every class, I don't know. I know some of you turned in some of these from last time, your assignment here can be do at least one of those you didn't do last time. Now, notice I quit at the discussion problems because my observation is very few, if any, of the discussion problems have answers in the back of the book. Okay? So you don't have to do those. If any of them do have solutions back there, by all means, try to see if you can do those solutions. But most of them do not. But that doesn't mean you don't need to look at them. Okay? For instance, I flip the page here and see that number 51 talks about the folia of Descartes. Now, that is a complicated looking differential equation they're asking you to do something with. The reason I pointed out to you is there's a potential paper topic, or two, or three. Number one, who is Descartes anyway? Now, most of you probably are familiar with him, but he could be a paper topic. It's mentioned in the book, certainly could be a paper topic. How did he come up with this folia of Descartes? That may be a lot harder to find, but if it's of interest to you, you might want to look into that. Or, and this would be, to me, would be a more practical thing, who in the world uses this folia of Descartes? Is it somebody in my field or some other field? You could do what are applications of this, or is it purely a mathematical exercise? It could be that. There may not be any practical application for it, but that's why I say if you are looking for a paper topic, don't forget to look at these problems too. You might run into something. Now, I don't know if any of you have access to a computer-assisted system, I think is what it stands for, a CAS. That would be something like, I guess, Maples or what's the other one that starts with M? I can't remember, but anyway, there's a few of those out there. We don't have any. I don't have any. If you happen to have those, you could easily be using something like that in your field of study or in further courses in your field of study, or actually when you get out into actual practice of what you're doing, you may be using those. Not a bad idea to try to follow what they're saying here. I don't have it. It's certainly not required, but if you want to follow that, you certainly can.
Do you mean like Minitab?
Say again?
Like Minitab?
Minitab may be one. I've seen that name before. I'm not at all familiar with that one, so that may be one. I've heard the term MathWorks. That may be one. I don't know. There's a bunch of them out there. If you have some that you use at your school or you have access to at your school, Dawson probably doesn't because we don't have anything like this, but if you just happen to have some and you want to practice on some of those, go for it because it probably will serve you in good stead in later courses or perhaps when you actually get in the field. You don't have to do it though, but if you have access to them and want to try, go for it. I probably can't help you a lot because I don't have access to it either. But if you are familiar with those, give it a shot. So any other questions? Good deal. Let's move on to 1.2. Okay? 1.2, the title of this is Initial Value Problems. All right. This is sort of similar to what you did with definite integrals. This is sort of a stretch here to say that, but it is. Remember, an indefinite integral, every time you did the integration, you always had to put as part of your answer plus c. What was that plus c? That was an arbitrary constant. Just like we were looking at before, C1, C2's arbitrary constants. Because an integration is basically undoing a derivative, a first order derivative. Okay? Now, so what we're going to do now, whereas in section 1.1, every example we had, in general, I believe, was left open for any fact. What's your general solution? General solutions, as we saw at the end in those endnotes, those require an arbitrary constant for every order of your different differentiation. Okay? Well, what we have in 1.2 is, and remember the curves. Remember that those curves that we showed, some went up, some went down. How you could determine which one you're really dealing with is just like they did in the book. They assign a value for C1, assign a value for C2. That defines this curve. Okay? A different value for either C1 or C2 or both defined a different curve. So what an initial value problem does, it gives you the differential equation, but it also gives you a condition subject to something. Okay? And if you got your books in front of you, I don't want to write this thing out here, but here is your, what they called this, I can't remember what term they used for it, general or natural or some sort of way to write the differential equation. Remember, one way is to use, say, a capital F, and capital F is some function of your independent variable and all your various derivatives of your dependent variable up to y sub n, y, the nth derivative of y. Or if you put the nth derivative of y, extricate that from the rest of them and put it on one side and then put a little f there, f of x, y, y prime, y double prime, up to y, the n minus first derivative. There is, and I can't remember what they named that. Let me go back and find it. They give these names and they're really not all that important except they're useful when you're talking about it like right now. The normal form, that's what it was called. The normal form, back on page 5, if you can turn back to page 5. That's your normal form for a differential equation. It's a general form. They're not telling you anything about what those derivatives are. They just say the nth derivative is a function of your independent variable and the dependent variable and all the derivatives of the dependent variable up to the n minus first derivative. But here's the difference. Subject to y at some value x0. Now, being a physics background like I am, when I see initial value, I think t equals 0. Okay? Always thinking in terms of time. That's what initial means to me. What they mean here is a little broader definition. This is I would call it fixed value problems, but they don't use that terminology. They call it initial value problems. So at some fixed value for your independent variable x, y at that fixed value has some fixed value, y0. Y prime at that same fixed value x has some other value. They happen to call it y1. Y double prime would have, at the same x value, would have some other fixed value, y2. And y to the n minus first derivative of y would, at that same value x0, would have some other y value, okay, which would be, they list as y sub n minus 1. Okay, where those y0, y1, y2, y3, up to yn minus 1 are your arbitrary constants. Not the c's that we used before. These are just arbitrary values that when x is equal to x0, these y's and y primes and y3 are these values of y. That's called an nth order, because it's nth order derivative, is your maximum derivative, initial value problem. And quite often from now on, I'll call it IVPs. Okay. I was part of an organization when I was in grad school called InterVarsity Christian Fellowship, and they had their own publishers called InterVarsity Press. So when I see IVP, I think InterVarsity Press, but that's not what we're dealing with here. Okay, this is initial value problem. So the values of y of x and all of its n minus 1 derivatives at x0, that's what your initial values are. Your x0 is your initial value for x, or your fixed value for x, and then all these others are your initial conditions. Now notice we don't put one for the nth derivative. You don't need one. You only need n of these values. Well, wait a minute. Do we have n? Yes, because your y0, that's from y at x0. So you have 0, 1, 2, 3, 4. So you're always one more than what your subscript is. So you do have n values. So if you have an nth order differential equation, you need n initial values, initial conditions. Okay. So let's say we have a function. We have no idea what the function is. dy dx is equal to some function of x and y. Because that's the first derivative, you only need to the n minus first derivative. Well, n is 1, so you don't, it's the 0th derivative, in other words, just y, f of xy. Okay? Since it's the first order, all you need is what the y value is when x is equal to its fixed value, x0. And that's going to be y0. Okay? Now, again, I'm going to turn the book up so you can see it. And you probably are seeing it already. All those are solutions for that differential equation right there. We don't know what the function is, but let's just say all those are solutions. But if you know that when x is equal to x0, y is equal to y0, if there's your point x0, y0 in the xy plane, that is the curve. That blue curve is the one. You don't have a family of solutions anymore. You have a particular solution, one single solution. And that's what initial value problems do for you. They eliminate the need for all those C1, C2s, and so forth. Okay? This one would only have had a C1. Okay. But if you had a second order differential equation, like the second one listed there, d2y is dx squared, that's some function of x, your independent variable, y, your dependent variable, and y prime, which is 1 degree less than what your left-hand side, which is second derivative of y. Okay? Well, because it's the second order, you need two initial conditions. And again, y at some fixed value for x, y0, x0, is equal to some fixed value for y. We'll call it y0. Now that y0 is not the same as the y0 before, and the x0 is not the same as before. This is for this problem. Okay? But then you also need the second one, which is y prime at x0, always at the same value, is equal to some other value for y. Okay? Now, in this case, you have a second order differential equation. If you had solved that to get a general solution, you would have had two arbitrary constants. You plug one of these in, and you eliminate one constant theoretically, plug the other one in, you eliminate the other. Sometimes it actually winds up that you have two equations, and you have two equations, two unknowns, then you eliminate those by that method, okay? What do we call it? Elimination by addition, two linear equations with two unknowns, okay? Now, this would be an example of what's going on there, okay? The bottom one, okay? Number one, now, to me, this isn't the best illustration, okay? Because technically, you could have several different of those solutions that pass through that same point, x1, y1, or x0, y0, that point right down there, okay? But only one of those has the slope that's y1, because that's what your second condition is, if I can find it here, there it is. I can't see it. I don't know if you can see it, but y1 or y prime at x0 is equal to y1. So only one of those would have the slope that would be y1. Okay, I thought the illustration here was less than adequate, okay, because what they show here, that x0, y0 would identify which one of those solutions you would have. No, you could have multiple lines going through that point, multiple curves going through the point, but only one curve would have that slope. So that's the reason you need both. You know, second order differential equation, you need both of those. Okay. Now, let's do example 1. Okay. Now, back in the homework exercises of 1.1, have you finished those yet? No, I'm just kidding. Okay. Example, problem 45, you were asked to, you haven't gotten there yet, but to deduce that y is equal to c e to the x is a one-parameter family of solutions for the simple first order equation y prime is equal to y. Well, yeah, certainly that works because the derivative of e to the x is e to the x. So y prime would be c e to the x. So yeah, y prime would equal y. Certainly that works, pretty obvious. Now, all the solutions of that family are defined on the interval from minus infinity to positive infinity because e is defined everywhere, okay? If we impose an initial condition, say y at 0, when x equals 0, y is equal to 3. You only need one initial condition because this is a first order differential equation. Then substituting x equals 0 into that equation, okay, what we've already said, the differential equation here is y prime is equal to y, okay? And the solution is y is equal to c e to the x. We know that works, okay? Our initial condition here, though, is y of 0 is equal to 3. So what you do, you plug in that to your solution. Y, which is 3, has to equal c times e to the 0. Anyone tell me what e to the 0 is?
1.
1. So that means c is equal to 3. So if c is equal to 3, that means your solution, your one and only solution, is y is equal to 3 e to the x. Okay? Now, here's the drawings again. Now, this is going to be tough because it's at the top of the page, and if I put it at the top of the page, then I have to talk around it. And I can't see that well. Can you get it closer? Okay. There are a bunch of curves. Looks like 6 curves. I can't see them on the screen. Is that the right one? No. Yeah, there it is. 6 curves there. When x equals 0 and y is equal to 3, there's the one and only one curve of those curves. Now, there's an infinite number of curves there.
Cutting out.
I'm cutting out? Okay, that's because I'm talking over here to the side, trying to talk around the book. I don't know if you see my face there. Okay, that's, I didn't know, this brand new computer that, well, almost new computer, just a couple years old, that replaced the ancient one I had before, I never had this problem of having to talk directly into the microphone. So I don't know, I apologize for this. This makes teaching even tougher. That ancient computer, no one ever complained that I was getting fading out because I talked so loudly. Now, doing the volume on my side isn't going to help you on your side, is it? That just, when
No, sir.
What, say again?
No, it doesn't.
No, it doesn't. So sorry. I can't do a thing here about it except try to talk right into the microphone. And it seems like to me the microphone must be down here at the bottom Because if I talk up here, I'm fainter. Down here, it's louder, right?
Yes, sir.
Okay, so I have to talk down there, and when I hold the book up that blocks it, then the sound waves don't get to the microphone. Okay, now in the B part of that problem, okay, it says if we demand that the solution curve pass through a different point, this time it has to go through the point 1, negative 2, okay, not 0, 3 as the last one did. It has to go through the point 1, negative 2. We take that and plug it into your same solution. Y is equal to C e to the x, okay? The y here is negative 2 is equal to C times e to the 1, okay, right? Because x is 1. So what is C now? That would mean that C is equal to minus 2 over E. Whatever that is. E is about 2.7 or so that's something a little bit greater than a negative or less than a negative 2/3, okay? And that would be the curve that was the red curve. I'll try to talk down to it. There, you see the red curve with the red dot in it? That is the point x equal 1, no, yeah, x equal 1, y is equal to negative 2. That would have to be your C then, is the irrational number, negative 2 over E. You can punch that in your calculator and see what value that is, but it's something on the order of negative 0.7, I think. I don't know if I'm just doing that off the top of my head. I may be wrong on that. Let's see. I'm using my phone, so I have to turn it sideways. 2 divided by E equal, yeah, about negative 0.735, something like that. 736. Okay. Not that that was anything special, but there is a value. That was your C in that case.
So we are plugging in different numbers for C in the equation y equals C e to the x.
Right. Okay. Is that what you're saying? Here,
okay.
We plugged in x equals 0 to that. There's your solution. Y is equal to C e to the x. We knew that was the solution. Okay. Plug in, instead of x, you put in 0. For y, you know you've got to get 3. So then for y, you put 3. You write down your C, e to the 0. Well, e to the 0 is 1, so C is obviously 3. Over here for this one, if I can find it, there it is. Here was the ordered pair. You say it has to go through 1, negative 2. Well, that means that when x equal 1, y has to be negative 2. So here's your function. Y is equal to C e to the x. Plug in negative 2 for y, C for C, x for 1 for x, so C e to the 1. Well, solve that for C, and you get C is equal to negative 2 over E, e to the 1. And E is a number about 2.7 or so. Irrational. So that's how you get that. Now your arbitrary coefficient becomes your variable, you might say, because you plug in values for the variable. Solve for the C. Is that what you were asking?
Yes.
Good.
So just making sure I was plugging in the right.
Yes.
So we're solving for C.
Right. Okay. Exactly. All right. So now, I don't know if you recall back in section 1.1, we always said you have to always define an interval. The interval is important. And this example coming up is going to illustrate this. And back in problem 6 of exercise 2.2, which you didn't have to do because that's an even number, it said, oh no, I'm sorry, problem 6 and 2.2 coming up, okay? You'll be asked to show that a one parameter family of solutions for the first order differential equation is this. Now, let me think I'll flip my paper over and do this. So here's your differential equation. And by the way, folks, you help me keep up with time because I'll just get carried away and keep on talking. We end at what, 11:40 or 10:45, right?
Yes, sir.
Okay, all right. So we got almost an hour. I inherited my wife's old Fitbit watch, and I just noticed the battery's going low. So let me take a pause here because I need to put this, otherwise it's not going to make any sense. I need a bladder break anyway. So if y'all don't mind, let's do a pause here. I'm going to pause on the recording so you don't have a lot of dead time here, but I'll leave the Zoom up. Let me dramatic. And are y'all still here? It looks
I'm
like
back.
we dropped somebody. It looks like we lost Billy. I don't remember if Billy has a class conflict or what, but I don't. Seems like there is.
She messaged me and said that she had another class she had to go to.
Yeah, I was thinking she might be. I knew I had a couple of students who had multiple classes, and since I record this one, hopefully she'll be able to follow it. Has anyone looked at the YouTube video to see if you can make any sense out of my holding, something up in front of the camera? Can you see that on the YouTube videos? Has anyone looked? Dawson, did you ever last term?
But
Were you ever able to see when you looked at I don't know if you ever looked at a YouTube video because you were there most classes, but did you ever look at one to see if you could pick up when I held a piece of paper up in front of the camera? Does that come across in the YouTube video is what I'm asking.
I haven't seen the videos, so I'm not sure.
Okay, all right. Well, if y'all ever look, let me know if the camera shots are helpful or not there. One reason I do them is so that people who are not in class, in case it does record those, they can sort of see what we're talking about. Because I know it's hard to follow when you're not here, and especially if they don't have books. And I'm not sure. We still haven't seen. I think Corbin came that first day, but went to the non-existent collaborate meeting, and Ricky was here last time. So I think everybody has shown up, but I don't know that any more than the four of you have books. So that's the other reason I try to hold up the things in front of the camera, in case they can see it, but I don't know if they can or not. So anyway, we're on page 16, chapter 1, Introduction to Differential Equations, section 1.2, initial value problems. And I was leading into example 2. And by the way, now that I don't have a watch on, I have no idea what time it is. I'll check every now and then on my telephone, but it doesn't keep the screen up there for very long. So don't let me talk over, okay? Because I've got another class coming up at 11. All right. So in problem 6 of exercise 2.2, way in the future, you'll be asked to show that the one parameter family of solutions of the first order differential equation y prime plus 2x y squared is equal to 0. Okay? There's a first order differential equation. Okay? Right there. This is going to be a flashback. See if you remember. What type of differential equation is that?
What do you mean by type?
Okay, that was 1.1. That's only two choices here, binary, remember? Ordinary or partial.
Got it, okay.
Okay, it's ordinary, okay, because the partial would have subscripts there, okay? What order of differential equation is this? First order, exactly. The only derivative there is the first derivative, okay? And then the third way of classifying, anyone remember what that third classification scheme was? Linear or nonlinear? Which is this?
Non-linear.
Nonlinear because of that squared right there of the y. If the x had been squared and the y not squared, that would be linear. This, however, is nonlinear. Not that it matters any, but I just wanted, since most of the others we've been doing were linear, I wanted to point out this is a nonlinear, ordinary, first-order differential equation. Okay? Now, there's your equation, and they say that the family, one-parameter family, how many parameters do you need in this one? 1, because it's a first-order equation. And here's what they say it is. Y is equal to 1 over x squared plus c. Okay? They claim that is your solution. Where in the, oh, here we go. There is your solution. Y is equal to 1 over x squared plus c. There's your one parameter, the c, wherever it is there. Goodness gracious, why can the pen not show up? Over here. There it is. There's your parameter c. Because it's first order equation, one parameter is all you need. Okay? And obvious is not just that, it's also one parameter, a nonlinear solution, obviously. Okay. That has nothing to do with it. Okay. All right. If we impose the initial condition that y of 0 is equal to negative 1. So here's your initial condition, y at 0 is equal to negative 1. Okay? Now, cynic that I am, I don't want to take their word for it. Let's plug that value in here and see if sure enough, oh, let's see, we probably can't do that yet, can we? No, we have to go on and solve. Okay, never mind. Okay, if we impose that condition, then you substitute x equals 0, y is equal to negative 1, and see what you get. So do that. So y is equal to negative 1 is equal to 1 over x equals 0, 1 over c. Huh, that's not too hard to solve. Invert both sides, you get c is equal to negative 1. Okay? So that's what we get as our parameter for that initial condition. Everybody see that? Make sense?
Yes, sir.
Okay. Now, so you've got that. Now you can go back and plug that into your solution. So y is equal to 1 over x squared minus 1, because c is negative 1. So there is your particular solution that satisfies that differential equation with that general solution. With this initial condition, there's the particular solution that works. Okay? Now, think back, put on your pre-calculus algebra hat. What would you think about that equation, that solution? That is a rational expression, right? And what did you always have to worry about with rational expressions? You have a polynomial in the denominator. What can the denominator never be? 0. So that meant you had vertical asymptotes where that denominator is 0. What values for x would give you those vertical asymptotes?
1.
1 would certainly work.
Negative 1.
Negative 1 would work. So obviously x cannot equal plus or minus 1, where our initial condition was x equals 0. So yeah, it didn't violate what we just discovered. Okay? Always check that. Okay? Now, here is where my cynicism comes in. Let's just put x equals 0 into this expression, and that gives you 1 over 0 minus 1. That should be minus 1. 1 over minus 1 is minus 1. Sure enough, that does work. So, we verified that indeed we've met the initial condition here. We should have. Everything was set up for us that way. Now, if you consider that function, though, remember we said x can't equal plus 1 or minus 1, okay? And we know that when x is equal to 0, y is equal to minus 1. If you were to graph, and I know I'll probably go out here. Okay, no, I can talk under the book here. Okay, there is how that expression graphs. See the vertical asymptote of x equal minus 1, x equal plus 1, and sure enough, 0, 1 is on that graph. It's not here and it's not there. So the interval for this differential equation with that initial condition is only from minus 1 to 1, not including the endpoints. Okay? So you have to specify that this solution that we're talking about is only good from minus 1 to 1. It won't work over here. It won't work over there because your initial value is here. You can't cross a vertical asymptote, okay? So you can't go outside the range. So that's an example of where the interval winds up being important because you only, and that's what they do in the lower figure here, then they show that for this problem, there is your solution. There's your initial value at 0, negative 1, and that's the only piece of that graph. This function here, this graph function here, fits your initial thing. Remember, it was y is equal to even your initial condition, 1 over x squared minus 1, but your initial condition has to be here. Can't be here, can't be there. The entire function is that one that's shown here, up here. But the only part that your solution is valid on is the part here between minus 1 and 1. That's why the interval is important. Or that's an illustration of why the interval is important. Okay? Now, so here is what they're pointing out. Considered as a function that you got, your answer was y is equal to 1 over x squared minus 1. That's your graph of the function, the blue graph up here. Okay? That is the graph of your function, which is your solution. But it's not the solution because as a solution for that differential equation, your interval is limited to that red part down below. So considered as a solution for the differential equation, it could be any part that fits, okay? For the one particular initial value we had, is the red part at the bottom. That's the one you use. So that's why interval is important. That one you'd have to specify between minus 1 and 1. That's the only portion of the graph that would satisfy that initial differential equation with that initial condition. Okay. I'm probably beating that into the ground, but it is a pretty important concept. So let's go to example 3, which is an illustration of a second order differential equation, an initial value problem, IVP. Okay? Now, example 9 that we did in section 1.1, you probably remember, I think this is where we started, or early on today. We saw that x equal C1 cosine 4t plus C2 sine 4t, we did this one today, is a 2-parameter family of solutions for this differential equation, x double prime plus 16x is equal to 0. We verified that and everything. Okay? Now, what is the order of that differential equation? Second order. Therefore, we had to have two arbitrary coefficients. We got them. How many initial conditions must we have to fully satisfy that? 2, okay? And what will they be? They'll be the function value at some given value for x. That's the at some value for t. T is your independent variable. So x, when t is some fixed value, but also the first derivative of x when you're at that particular value, okay? So they say find the solution for this initial value problem. Same second order differential equation. And here they tell us that x at the value pi halves, I appreciate them using that, is equal to -2. And the x prime, always at the same place at pi halves, and its value is 1. Okay? Now, what do you imagine we're going to do? Plug it in. First, we'll plug in when when t is equal to pi halves, that's the independent variable, your x is going to be -2. So I'll write that down. -2, that's the x, is equal to C1 times the cosine of 4 times pi halves. That's going to be 2 pi, right? 4 times t. T is pi halves. 4 times pi halves is 2 pi. Okay? Plus C2 times the sine of 4 times pi halves is still 2 pi. Now this one is a very easy one to deal with. What is cosine of 2 pi? Anybody? Oh, we don't have to remember trig, do we?
0.
No, cosine of 2 pi is 1. Remember, cosine starts at 1, goes down to 0 at pi halves, and goes down to -1 at 3 halves pi, and then comes back up to, at pi, it goes down to -1 at pi, back up to 0 at 3 halves pi, and then goes back where it started, 1 at 2 pi, because the period is 2 pi. Remember? So that's 1. So this will be -2 is equal to C1, because cosine of 2 pi is 1, plus C2. What sine of 2 pi? Dawson, this is your turn again. 0. Okay, sine of 2 pi is 0, so therefore you don't have a C2 in this. So C1 is equal to -2. Okay? Well, that just gives you one of your parameters. So what we have to do now, guess what, is take your first derivative of your original function. So x prime for any value of t is equal to what? Take the derivative of that solution function. What do you get?
Can you rephrase that?
Okay. All right. Here is your solution function. Okay. X is equal to cosine 4t plus C1 cosine 4t plus C2 sine 4t. Okay. Your differential equation is x double prime plus 16x is equal to 0. Your initial condition is x at pi halves. When t is pi halves, x is -2. And when x prime at pi halves, because you have, this is second order, you need just when x is equal to a fixed value and x prime is a fixed value, is a pi halves is equal to 1. Well, it was easy to plug in to this one. X at pi halves is equal to -2. You just plug in up here when t is equal to pi halves, you calculate what x is. And that had to be -2. So -2 was that. So, okay, now I started writing the answer for the second one. The second initial condition is x prime at pi halves is equal to 1. So therefore, we have to take the first derivative of this function. And that's what I was doing down here. So what's the first derivative of any t, value t, dx dt for this function here? So take the derivative of this function. What do you get? X prime is equal to what?
Negative 4 sine.
No, C1, don't forget your C1. Negative 4C1 sine 4t, perfect. Continue.
Plus 4
Plus 4C2
cosine 4.
cosine 4t. All right, someone remembers the first, the Cal 1. Okay. Now we plug in what that initial value was. X prime at that value is 1. So 1 is equal to, now we already know what C1 is, so let's plug that in. C1 was negative 2. Remember, we already determined that. So negative 4 times negative 2 would be 8 times the sine of 4t. I left off my t. Well, when t is equal to pi halves, 4t is 2 pi, just like it was before, still is. Sine of 2 pi is still 0, so who cares about that 8? The sign is 0 there. Plus 4 times c2, and what was the cosine of 4 times pi halves?
1.
1, okay. So your equation now is 1 is equal to 4c2, right?
Yes.
Okay. Solve for c2. c2 is equal to 1/4. Okay. So what is your solution? Go back to your original solution. X is equal to c1 negative 2 cosine 4t plus 1/4, that's your C2, sine 4t. Now I write all over a piece of paper, so this is going to be a little hard to follow. But hopefully you were doing the writing at the same time. Okay, we had already figured out, whoops, wrong problem, that C1 was equal to negative 2. We took the derivative, and that's what you said. I wrote it down. Okay, I almost left off my t. That's why it's crowded there. And then I plugged in, when t is equal to pi halves, the sine of 2 pi is 0, so we didn't even use that 8 there. And we had 4 times c2, so c2 was equal to 1/4. Okay, we take that and c1 equal negative 2, c1 is equal to negative 2. We plug that back into our original equation, and there we have it. X is equal to, C1 was negative 2 cosine 4t plus C2 was 1/4 sine 4t. There's your particular solution that satisfies that initial condition, those initial conditions. C1 equal X at pi halves is equal to minus 2, X prime at pi halves is equal to 1. Does that make sense?
Yes, sir.
All right, good deal. All right. Okay. Now, and in the book, you'll see that's the answer they got. Top of page 17, hence x equal negative 2 cosine 4t plus 1/4 sine 4t. Okay. When you have an initial value problem and you have enough initial conditions to match the order of your differential equations, you should come up with a particular solution. No arbitrary values in it, no arbitrary coefficients in it. Now, the book now turns to muddying the waters, I call it. Two fundamental questions arise in considering an initial value problem. First question, which I know popped into your mind, does a solution of this problem even exist? Okay, that's the first question. The second question, if it does exist, is it a unique solution? In other words, is there some other solution hiding out there somewhere? Okay, well, the problem we just did sort of indicated, yes, there was a solution, we found it, and hopefully it sort of helped you feel good. Yeah, this seems to be the only solution that would fit those conditions. Okay? So basically, the first question is existence. The second question is uniqueness. So for existence, does the differential equation dy dx equals some function of xy possess solutions? Does a solution really exist? Second question, do any of the solutions curves pass through the point? Okay. Okay. I'm not really sure what they're driving at here. Perhaps that first question, does the differential equation dy dx equal f of xy possess solutions? Now that indicates it's not an initial value problem, it just is a differential equation. Well, yeah, arbitrary coefficients, yes, that's the question. With arbitrary coefficients, does it possess a solution? Now, if it's an initial value problem, and it's a first order one, do any of those solution curves that you may have found in the first part actually pass through the point x0, y0? That would be, both of those are part of your existence. Does the differential equation actually possess any solutions, arbitrary solutions, okay? And if it does, will one of those solutions pass through the point in question? Okay. Now let's go back just in general. Remember, it wasn't that long ago, this problem. What if we saw that there are solutions for that differential equation? They would fit graphs that look something like that, okay? But what if we said, does this have a solution at the point 1, -3? What would be your answer? Hopefully it would be no, because at 1, you have a vertical asymptote. So no, it doesn't have a solution that passes through 1, -3 or 1 anything, because that's a vertical asymptote. So that would be a situation where you would have they have a name for that. Let me think what it is. An ill-posed problem, because that point is not on any solution curve. Okay? So that would be answer your second question there, no. Okay. Now, uniqueness. When can we be certain that there is precisely one solution curve passing through that point, that there's not another one? Okay. Now, in example 1, I don't know if you noticed this or not, but 1 and 3, the phrase a solution is used rather than the solution. I didn't even notice that. I usually try to notice that. But on example 1a, it says, thus, y is equal to 3e to the x is a solution for the initial value problem, y prime equal y, when y of 0 is 1. Y of 0 is 3. Okay? And then on the second one, they said, in this case, y is equal to -2, x to the -1 is a solution for the initial value problem, that one, okay? It says a solution. Now that would sort of suggest to you there may be some others out there, okay? Example 3, it says, find a solution for the initial value problem. Just their wording there suggests, and their answer, hence, x equal -2, cosine 4t, blah, 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 is a solution for the problem. Okay. Now, was there a reason for that? The indefinite article a is used deliberately to suggest that the possibility of other solutions may exist. At this point, it has not been demonstrated that there is a single solution of each of those problems. The next example illustrates an initial value problem that actually does have two solutions. And this is one we've actually talked about before. Okay? And let's see if I can find it on. Yes, here it is. I think it is. Yeah, there it is. Okay, here's the problem. We've hit it before. That y is equal to 1/16 x to the fourth and y is equal to 0 are both solutions for this differential equation. dy dx is equal to xy to the 1/2. Remember we did that one earlier. We verified both of those were solutions. So even though in your initial condition that when x equals 0, y is equal to 0, it works for this one and it works for that one because y is always 0 in that one. Okay. Now, here is the graph that's showing what's happening there. Is that it? I think it is. Okay. Remember, the graph there was a quartic function. Okay? But also, y is equal to 0 is the red line there, the x-axis. Both of those are solutions for that initial value problem. They both intersect at 0, 0. Okay? But they're two completely different solutions. Given any other x other than x equals 0, they don't match up. The y equals 0 is always going to be 0. The y is equal to 1/16 x to the fourth is going to be some other value for any other one that you put in there. So that's a situation in which you have two solutions. Okay? At least two solutions. And if you remember back when we did that problem, it actually had another one. I'm going to flip back to 1.1 when we did it. Remember? That was a solution. And remember? That was a solution. That's that same problem. Okay? So it has many solutions that all fit that initial condition. Okay? X equals 0. Y is equal to 0. Okay? Now, they introduce all that, and here's what they say after that. Within the safe confines, the safe confines of a formal course in differential equations, one can be fairly confident that most differential equations will have solutions and that solutions of initial value problems will probably be unique. So for the existence part, most will have solutions. And for the uniqueness part, will probably be unique. Those aren't very reassuring words, are they? I guess adverbs, I guess, in both cases. Real life, however, is not so idyllic. Therefore, it is desirable to know in advance of trying to solve an initial value problem whether the solution exists, and when it does, whether it's the only solution, whether it's unique. Since we're only going to consider first-order differential equations in the next two chapters, we state here without proof a straightforward theorem that gives conditions that are sufficient to guarantee the existence and uniqueness of a solution of a first-order initial value problem of the form given in equation 2, which is back on bottom half of page 15 at the very beginning of this thing. We shall wait until chapter 4 to address the question of existence and uniqueness for second order initial value problems. So here is that uniqueness. If you got your books, I don't want to hold it up, but I will if you don't have your book in front of you. Here's the situation. Let R be some rectangular region in the xy plane defined by x is between A and B, and y is between C and D. C at the lower part and D at the upper part. So here you have this rectangular region, x equal A, x equal B, y is equal to C, y is equal to D. Okay, that defines some region, R. Okay? Contains the point x0, y0. Somewhere in that region is that point x0, y0. If f of xy and now here we hit a partial derivative. We're not doing partial differential equations, but we do hit a partial derivative. F of xy, that means f is a function both of x and y, meaning both of those are independent variables, so you can only take partial derivatives. If the partial of f with respect to y, if both f of xy and the partial of f with respect to y are continuous on that region R, then there exists some interval I0, and I0 is some region around that point x0, y0, plus or minus h on this side, and that's all we're worried about, plus h minus h, okay? Contain on that interval between A and B, and a unique function, so many ands here, a unique function y of x defined on y, on I0, that the solution of the initial value problem. Okay, blah, blah, blah. Let's go back and say that. If f of xy and the partial of f with respect to y are both continuous on R, then there does exist some interval in that region around your x0, y0, where your x plus plus h and x minus h are there for h greater than 0, contained on that interval from A to B. And there's a unique function y of x defined on that interval A to B. There is a solution for the initial value problem. So that's your existence. Okay. This is really a lot of blah, blah, blah. Don't get too bent out of shape over it. Most of the time, I hate to say it like this, most of the time, it'll be hopefully somewhat obvious, or it won't matter. Okay, let's leave it like that. The foregoing result is one of the most popular existence and uniqueness theorems for a first-order differential equation because the criteria of the continuity of your function of f of xy and the partial of f with respect to y are relatively easy to check. Okay? The geometry of theorem 1.2.1 is illustrated in this figure here. And again, I'm not certain, this is hard to talk around, okay? I'm going to try to talk around it. There's the figure they're talking about, okay? There is the region, x going from A, I don't know if I can get my finger up there, to B, y going from C to D. So there's the blue region you're talking about. Pick a point x0, y0 somewhere in that plane, and if the function is defined there at that point x0, y0, and the partial of f with respect to y, which is basically the slope there, is defined, then you are fairly confident it has a unique solution. Okay? Let's just leave that alone. Okay? So let's go back and revisit example 4. That's the one that had multiple solutions, it appeared. Okay? Now, we know it has at least 2 solutions. I pointed out it has more than that. It passes through 0, 0. So let's look at those functions. I don't think I want to write them down again.
Just an FYI, Professor, we have 10 minutes left.
10 minutes. Okay, great. Thank you. Okay. You're wanting me to hurry up, I bet. Okay. Let me find, if I can, those functions again. Is that it? Nope. Yuck. Yep. There it is. dy dx is equal to x y to the 1/2. And there's your differential equation. And that's the one that has two solutions. Okay? Let's see if I can find those on this same page too. Y is equal to 0. And no, that's not it. That's a different problem. Yeah, there it is. Nope, different problem. I can't find, well, there they are. Y is equal to 1/16 x to the 4th, and y is equal to 0. Both of them are solutions. Well, let's see that function of x and y, x y to the 1/2. That's your derivative. dy dx, that's the function f of xy in what they call normal form, remember? Okay, let me find it. There it is. We just put f of xy here and equal to that. Okay, that's the normal form. Now, the partial of f, the partial of this is now f, of that with respect to y is going to be, let me do it, okay? Sort of fun to let them, but let's do it. I'll write that down again. Remember, when we write this, is derivative of y with respect to x is equal to x y to the 1/2. That was our problem. Now remember, the other way we do that, when we write that in what they call normal form. Now, I told you it's not going to be all that important, but they don't use the term here, but that's what they're doing. They're saying that's your f of xy. So f of xy is equal to x y to the 1/2. Okay? Now, remember what the conditions were? That f of xy be continuous on the region R. Okay. Now, if you think about that for just a moment, the region R that would work, okay, I wrote it down here. Yeah, right there it is. Okay, the region R that would work for this, that would only be continuous when y is positive, right? Because you can't take the square root of a negative number. X could be anything, positive, negative, fraction, decimal, it doesn't matter, but y would have to be that, because that's your f now. So y would have to be positive. Well, the region they showed in the blue box that I showed before was all y's being positive. So for that region, you're okay there. But the second condition is at the partial of f with respect to y, what would that be? Okay, do you remember how to do partials? Partial of f with respect to y, if that's your f, x, y to the 1/2, what's the partial of f with respect to y? Well, you treat x as if it's a constant, remember? Cal 2, okay? And I think it's Cal 2, maybe Cal 3. I think it's Cal 2. 3, Cal 3, okay. So treat x as a constant and take the derivative with respect to y, which would be 1/2 y to the minus 1/2. So when you take that partial with respect to y, your x is on top, your 2 is on the bottom from the 1/2, and then the square root of y is on the bottom too. Okay? So it's probably not the best way of writing it, but it's certainly one way of writing it. There's your partial. X over 2y to the 1/2. Now, is that continuous on your interval? Well, the blue box that we showed here, now we know that not only can y not be negative, now y cannot be 0 either. Okay? So that means you have to confine yourself to the region that y is greater than 0. X can be anything, but y has to be greater than 0. So therefore, now when we look at our solutions, remember the solution that we saw here that was a problem? Remember, now we have to confine ourselves either to the region over here where y is positive, or the region over here where y is positive, but you can't have y is equal to 0. So we lose the issue that y equals 0. That was, remember, we called a singular solution. Not in the problem now, because that partial required that that the function be defined. In other words, you have to have only positive y's. Well, that's pretty obvious here. Okay, but now with the partial, that means y can't be 0 either. So you can't have y equals 0. You have to be somewhere in this region here, or somewhere in this region here. You just can't be both. Okay, so sure enough, if you meet those two conditions, you can be fairly sure you do have a unique solution now, not a ambiguous solution like we did before. Okay? A lot of blah, 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 right? Now, going back to example 1, and example 1 was those y is equal to e to the cx. Remember, that was this problem. Okay? That one, whatever initial value you meet, it's going to be unique. Okay? Because there aren't any ambiguities there at all. Okay? I don't know why they brought that up here, but it is. In example 1, theorem 1.2.1 guarantee there are no other solutions to the initial value problem when y of 0 equal 3 or y of 1 equal to negative 2. Those were the only two. Okay. And when you do your function, the function is y. Alpha of xy is equal to y. That's defined everywhere. And the partial of alpha with respect to y is 1, because the derivative of y is y. That's continuous throughout the xy plane. So therefore, your interval is from negative infinity to 1. Now, I forgot to say it on the first one. The interval for which that x, y to the 1/2, the one we were looking at before, it would have to be y has to be greater than 0. And then you just pick your x. The x would either have to be on the positive side or the negative side of 0. It couldn't be at 0 because they're y0. All right, okay. That leads then to, let's see how we're doing on time, 2 minutes. Okay, the interval of existence and uniqueness, suppose that y of x represents a solution for an initial value problem. Okay, the following 3 sets of real x of the real on the real x-axis may not be the same. The domain of the function y of x doesn't have to be the same as the interval on which the solution exists. So we saw this before. And the interval of existence, I0 of existence or uniqueness. Okay? So what it's saying is you may have 3 different things that look similar but may be different. Domain of x, that would define anywhere that the function is defined. Your interval over which the solution is defined may be pieces here or here or here, okay? That may be true, but the interval of uniqueness where that particular point is, it's usually going to be this piece, or that piece. It can't be any of the other, okay? So all three of those are slightly different in meaning. So you can read that. It basically is harping on the same thing over and over again. We have reached the remarks, and the remarks introduce another type of problem that unfortunately you do run into in work situations sometimes. Those are boundary value problems. For an initial value problem, the X value always has to be the same. For a boundary value problem, you could have a boundary here and a boundary there. X is one value here, another value here. That's something that's realistic in the work world, but it makes solving your differential equations much, much harder. They don't guarantee, and those are called boundary value problems and boundary conditions. They do not guarantee unique solutions like initial values. We just finished 1.2. Homework exercises here would be 1, either 3 or 5, any of the odds either 7 or 9, either 11 or 13, do 15, any of the odds 17 to 23, 25 or 27. Goodness, there's a pile of them, aren't there? Any of the odds 29 through 33. Any of the odds 35 to either 35 or 37. And any of the odds 39 to 43. Okay? You don't have to do them all. Okay? Do enough so you feel comfortable that you've got this down. Okay? So when I said the homework exercise that you need to submit, just pick one of any of the ones in 1.1 that you didn't do last time, or any of the odds in this one that you obviously didn't do last time because we didn't discuss it. The discussion problems, again, worth looking at, and if the answers are in the book back, you might want to consider doing it, but generally the answers are in the back. We'll begin next time with 1.3. Any questions?
No, sir. Thank you.
So
All
thank you
right.
very much.
I'm sorry we ran over 2 minutes, but guess what? I'll not charge you any extra today, okay? So, we wound up with just the 3 people here because Billy had to leave, so a total of 4 were here today. Appreciate your attendance. I want you to have a good weekend, and of course, doing differential equations will make it a great weekend, won't it?
Yes, sir.
Good deal.
Yes.
All right. Take care. I'm going to end the recording. I'll also let me end the recording first.